Hello everyone, how's it going? No, this is not a park and bark, even though I am on my usual park and bark scenario. You can likely hear the rain outside. I apologize in advance, but hey, I gotta record this. And today we're gonna be making a Screenspace anchored shader. This is something that I use all the time. Okay, this technique was made by an epic technical artist, I believe. If I do find the original write-up on the technique, I will put it on the link in the description. I don't quite remember where I found it. I just have it on my Obsidian notes somewhere, and I thought I would share because once again, it's an effect that I use across plenty of other shaders. It's an incredible technique. Essentially, you have a Screenspace UV so that you can make VFX independent from the UV unwrap of the model, but it is anchored and scaled by the object. So as you move the object around, it is as if the UV, although in Screenspace, is actually attached to the 3D model. It's a really important technique, and this video is going to be referenced in future videos. So this is a foundational piece of knowledge that is paramount you understand. In this video, not only do I teach the actual technique and not only do I teach the actual material function, but I also take the care to explain bit by bit and explain a little bit of the math behind it, the logic behind it, why things work the way they work. And hopefully this will be very insightful for all technical artists out there. I'm sure many of you already know this technique, but hey, there's a lot of people starting out that don't know this technique yet. So please enjoy the video. Alright, so I have a material here, just surface, opaque, and lit. Stock Unity material. I'm using 5.2. This knowledge is agnostic to any version. I think it will stand the test of time, if you will. So what we're going to do here first, before we go into Screenspace, I think it would be interesting for us to try and do the logic that we want to do in world space. And then we can take that away, the key concepts from that, and apply those concepts to Screenspace. So we're going to stabilize a UV that's not going to be based on the UV of this actual model. It's going to be based on the UV of the rolled position. So, of course, we're going to need rolled position. And we have this node here. Now, if I click on Start Previewing Node here, you're going to see that our screen is going to be flashing these incredibly bright colors. This is because the absolute rolled position uses pretty high values. After all, the Unreal rolled is pretty damn big. So these values get very silly very quickly. So what we can do here is that we can multiply it by a very low value, or we can divide it. I'm just going to divide it because then we can use a smaller value. So let's try 400, clean 400. So I'm going to attach this to the emissive color here. So if we start previewing this node, 600. Yeah, this is more reasonable, I think. I'm going to make this unlit, the preview here. So we can see that we have now this cube with these gradients here, and these gradients represent vectors, right? So the actual positional vectors on the engine. But interestingly, so this is right now at 0, 0, 0. So if I move this about, you can see that these colors are going to change to reflect the rolled position that this object is in, right? You can see here how that is, changing the colors. The same goes if I scale. For example, you can see that it displays more and more of this giant gradient. And this giant gradient here, by the way, is sort of an UV kinda. Because you can turn this into a UV, right? I mean, pretty much any gradient that goes vertically and horizontally could be turned into a UV. So this means that we have a rolled space UV for this cube, but it currently doesn't really respect the boundaries of the cube, meaning the scale, and it also doesn't respect the translation of the cube, so the position. Now, a really cool trick that we can do here to address the position, which is very, very simple, is that we can just take our object position on rolled space. So here we have this position, and if we subtract them, I was writing shaders on Unity, so my hotkeys are a little bit sloppy right now, and we start previewing this node, what we're doing is that we are taking the absolute world position of this object, and whenever we're subtracting it, we're changing the starting point of this absolute world position gradient. And since we're constantly changing this pivot point to be equal to the object position, right, to be relative to the object position, then we are essentially locking that gradient that I showed you before into here. Alrighty folks, Leo from the future here. I decided to record a little bit of extra tidbit explaining a little bit better the relationship between the world position node and the current object position. And the reason for that, it's because it's actually something that we can visualize on a Cartesian plane. So here we have the world position pivot point. So this would be a top-down view of where the Unreal world begins. And you can see here that this is settled at 0, 0. And here we have our object, our cube, and in this case, the cube is on the 5 position, right? This is the 5 position alongside the x-axis and the 5 position alongside the y-axis. So here we have the current local position. Now, what we want is that this world position pivot point here holds a gradient on the y. Well, it holds a gradient on all vectors, but we are interested on extracting this gradient that is starting at this point, and we want to move it over here, right? So we essentially want this point to be here. Now, the interesting thing is that if you notice here, this is at 5, 5, right? So let's suppose that I take my cube and I subtract one positional point on the x and on the y axis. So what is going to happen if we do this is that you're going to realize here that I have this line, right? Look at this line here. So this right now is at 5, 5. If I subtract 1 from each axis, you can see here that our x is going to go to 4, 4. So this means that when we subtract a value from a vector, we're also moving it. So I can actually use these sliders here on the side. So I have my 5 and I can move it to be 4. And I have this 5 and I can move it to be 4. And voila, now we have moved our current local position on the actual space on the Cartesian plane. So the interesting thing is that if we take these actual values here and we subtract them by the pivot point, we're essentially going to be moving the pivot point to our current object local position. So this only makes sense, right? Because if you think about it, once again, we can take our little example here on this little line. Our current world position pivot point is at 0, right? So if we subtract it, as we are subtracting these values, it is getting closer and closer. And if they get subtracted to a point where, you know, they are subtracted by the current local position, since this is 0, 0, this is going to go to the same point as the current position. Now, this can be represented. I created this little function here, which just takes the points C and D and thus minus AB, right, which is our positions on the Cartesian plane. And you can see here that I can turn on the label. This is our new world position pivot point, right? And interestingly, I can prove to you that this is going to work regardless, because if I enable animations here, oh god, hold on, stuff to click with the pen. If I enable my animations here, you can see that now the pivot point, the object current position is as if I was moving the cube around, and as I move the cube around, you can see that our new pivot point is always following along. And remember what I told you? This cube actually holds a gradient, right? This little guy holds a gradient. So now the gradient is following along with our current local position. And this is why the effect works. This is why the pivot point is now locked to our cube. It's because we are essentially doing exactly the same that I'm doing here, but instead of doing it on the 2D space, we are doing it on the 3D space. Hopefully this visualization gives you a better grasp on what I mean by, subtracting the vectors and moving them around since we are doing the subtraction. So let's slap this here into this divide. I don't really know how high this number is going to be. I think it's still going to be silly. Let's save here. You can see we have the same gradient as before, but now if I move it, we're not changing colors anymore. The gradient stays the same because the starting point of that gradient is now always the position of the object. Pretty cool, right? Now, there's still a problem. Look, if I scale it up, we get into the same thing we were getting at before. It's just expanding into the abyss of infinite gradients. So, once again, it's relatively easy to fix this. Unreal has a default node called object bounds. And this object bounds, let me see here if I can display it. Not really. But this object bounds is essentially the scale and the actual position of this object relative to its pivot point. So we are essentially sampling how large this object is, which is of course affected by scale relative to its pivot point. So since we have essentially the volume of the object, right, the bounds of it, we're going to be able to fix our scaling problem. Because right now, if I put this here into base color, 1 second, save it, you can see that as I scale this, the rolled space position kind of just goes on and on and on forever. And we don't want these values to just infinitely increase as the rolled position generally does. So let me reset my cube here. So to do this, we're going to have to essentially use this as a multiplier ratio for our gradients that we have. So one interesting thing here that I kind of want to show, let me put this on the cube again. So we have something called debug float 3 values. All right. So if I start previewing this node here, we're going to see we're going to get some numbers. So these numbers are the bounds of this object, whatever object it is attached. So you can see here that this is 128. So this cube has 128 length in all of its directions, right? And all of its 3D translatable directions. If I go, for example, towards my sphere here, sphere is 160. So this is like the volume of the sphere on all of its axes. And therefore, if you look at the plane, much like the cube, has 128, but it has 0.0003 in one of them, which I believe is just a rounding error, if I'm being honest. And it makes sense because a plane is just like infinitely thin, right? It's just the limit of thinness. So it makes sense that this is going to be 0. But remember what I said here, that we want to use the object bounds as a multiplier for this? Well, on our gradients, we don't ever want to have 0 in there because that is just going to completely destroy the gradient. What we're going to do here, the first order of business that we're going to actually do is that we're going to use something called a max, and we're going to put it 1 here. So this essentially bottoms out the bottom value at 1. So you can see here that our plane, even though it is infinitely thin, it is now set to 1 on the x-axis, whereas before it was set to, 0 point something. All right, great. So what we're going to do here is that now we have a value that can be used as a ratio, as a multiplier ratio for these things. But actually, we're just going to divide it. We're not multiplying it. So division, as you all know, it's kind of the opposite of a multiplication in a way, kind of, sort of. So we're going to divide our gradient, our rolled position, with the pivot point set to the object position, and we're going to divide that by the object scale. And whenever we do this, we're kind of clamping our gradients. So whenever we do this, you'll be able to see here that I'm going to plug this once again on the emissive color, not the base color. Sorry, this divide, not that other one. And you'll be able to see that it's not going to be super bright anymore. Hooray! Look, and you can see that it's, even without the division, it's not like super blindingly bright, right? And also something else is that now you can see that these values, whenever I scale up my cube, I am no longer increasing the values into infinity. No, I'm actually scaling the gradients. I'm actually taking these gradient values and stretching them out to fill the actual bounds of the object. But these UVs here, they're not really usable, right? Because they go too much into the negatives. They're kind of going, you know, here from the bottom view, we can kind of have our more traditional UV set. Like, traditionally, you only care about this region here of the UV. You don't really care about these other quadrants. I mean, they're still usable, but those are usually the values, you know, that are the tiling values of your UV sets. This here is black because this is negative, right? Bleeding over into the negative values. So the way we can do this is that we can actually add the bounds themselves to this, and on vectors, like on 2D vectors, this is very visible, like Cartesian planes. Whenever you're adding or subtracting something, not only are you changing the numbers, but if you put those numbers on a Cartesian plane, you very quickly realize that whenever you add or subtract, you're actually moving things on the Cartesian plane. And the same is true for 3D. So whenever we add the scale to our gradients, we're actually shifting the actual position on the 3D rolled. We're translating it over by that amount. So right now, you can see here, this is very visible on the center. So you can see here that each one of these faces of the cube has kind of a cross formation, right, of colors. And right on the center, you have all the colors meeting each other, right? You can see here, this is where the black meets the green, meets the yellow, meets the red. So when we add our bounds to this subtract here, one second, add it over here, and we're going to place this on the divide, and you'll see that they'll be shifted. Now they're going to be on the corners. You see? Now the point where all the colors meet is no longer in the middle. Now it's right here on this very edge. And you can see already a more familiar face popping up. This is the traditional UV. Like if I take here, for those who are unaware, if I start previewing a texture coordinate node, you can see that this is like the traditional UV set, right? That most 3D models use for their coordinates. And here it is, right at the bottom. And all of these are actually valid UV sets. They're just different colors because they are on different ASICs, right? Because this is a 3D model and not a 2D plane. So this is essentially the logic that we're going to apply to our Screenspace shader, right? So we're going to have a screen position, we're going to have the object position, and we're going to try to essentially move the screen position alongside the object's movement. And then we're going to have to adjust it for the object's scale. It just so happens that we're also going to have, on the Screenspace case, we're going to have to adjust by a lot of other things. So this is why I wanted to first introduce the concept on a simpler environment, which is this one, and then we can go to the more complex Screenspace example. Alrighty folks, on to the next step. So let's start to create our Screenspace UVs here. So before, what we did is that we took the world position and we subtracted that by the object position to anchor it. So surely if we want to do it on the screen position, we could just take this, subtract by this, and voila, we have it done, right? Well, not quite. You can see here that we get errors thrown our way. So we do want to do this, but we got to make some conversion work first. On our object position here, well, actually, let's start previewing our screen position here. You can see that we have a gradient, right? And this is 2D. And if I move this about, you can see here that at the very, very edge, we got darker values. Darker colors means that they're closer to 0. So those are lower values, right? And if I go over here, we have brighter values, which means they're closer to 1. So it's a gradient that goes from, black to white horizontally and vertically. This is essentially the bread and butter of UVs. All right, this seems pretty. Now, how can we use this on the object position? How can we extract a 2D coordinate system, much like this one, from an object's position? Well, there is something called clip space on the rendering process. Now, I'm not going to get too deep into it because clip space is one of those things that unless you're actually making an engine, for example, you're not going to really interact with it much. But the gist of it is that your camera has a view selection, right? What the camera can see on your 3D application, and that camera has a range in which things are too close to be seen, and a range in which things are too far away to be seen. Not only that, but this camera does not have infinitely wide vision. So most cameras, for example, can't see what's whatever behind them. What happens is that this space, this imaginary space where things are not close enough, but not too far away, and also somewhat in front of the camera, inside of its view range, right? This is called clip space. So clip space also decides, for example, what gets rendered. So if there's a 3D model and some of the triangles of that 3D model are inside of these bounds of visibility of the camera, they get rendered. If the other triangles are outside of these bounds of visibility for the camera, they get discarded, so they're not rendered, which is also a way of optimizing your game. So this means that clip space is a region that needs to be able to assign a value to determine whether or not you are on the conditions to be visible by the camera and thus proceed with the rendering. This is a pretty high-level overview, but should be enough to give you the gist of it. We can take the object position and we can use transform to clip space. Yeah, transform to clip space. That's the name. If I take a look here, let's once again start previewing this node, and we have something pretty similar to what we had on the screen position. But now, if you pay attention, these values are far more extreme and very, very different from the other values. And we can actually take here this clip space XY, right? And we can take this screen space XY and we can do a debug float 2. After all, XY, it's a float 2. And if we start previewing this node, we have here those true values. And you can see here that as I go down below, we have a negative green value, and here it is flipped. Now, if I go to my viewport UV here and I put it on the debug, we can see that we have pretty low values overall on both of them, and here we have pretty high values. So you can see that there's a disconnect between those two. One of them treats one edge of the screen as different presets as the other. You'll also notice that this goes pretty deep into the negative values. This goes beyond 0, while screen position didn't. So there are some fixes for that. So let's fix that. Let's first get equivalence between the clip space XY and the screen position. So what we're gonna do here is that, well, the green value was flipped. So that's pretty easy to fix. The way we're gonna do this is that we're gonna drag this out. and we're going to multiply it. We're going to create a new vector 2. After all, this is a vector 2. It's an xy value. So here we have the x value and the y value. The x value was equivalent between screen position and transform to clip space. Of course, they were with different ranges, but they were not flipped. So we're going to multiply it by 1. And as you know, everything multiplied by 1 is itself. The other one was flipped, and a way of flipping it is by multiplying it by -1. After all, if everything multiplied by 1 is itself, everything multiplied by -1 is, well, a flipped version of itself. So we're going to multiply it here. We also have another problem to solve. I mean, we can, once again, go into the debug float 2, and let's start previewing the node. And we have here, you can see here that there's this 0.74, 0.5. We're going here. These are they're somewhat equivalent, but you notice how the numbers are different? Why are the numbers so different if it's in the same position? Well, this is because this is roughly double that. So we can divide it by 2, or we can multiply it by 0.5, which is essentially, turning it into half of itself. And now we still don't have numerical equivalence between them, but their ranges are the same. Now, interestingly, I just now realized that, of course, these things are not going to be, these numbers are never going to be the same. I apologize, because this also takes the object position itself, so the pivot of this thing is also counted into the mix. So I apologize for trying to get equivalence between those two, but this is still the correct logic because now they are on the same range. So before this went into the negative values, this went into a range that was -1 and 1, and now the combined range of these multipliers is going to be a total of 1, right? It's never going to be a situation where the maximum and minimum range for these values here is higher than these. That was the goal. But indeed, those values are never going to be quite the same because object position takes the pivot point into account. A little bit of a brain bug there. But now, if I take these two, once again, whenever you're taking things and subtracting them, you're also moving them on the Cartesian plane. So this is what we're going to do. We're going to move our screen position by our object position, now that we have actually adjusted it in a way that it is mathematically equivalent. It's on the same level of equivalence. So let's put this here into the emissive color. Now that should work. However, we're going to have a problem here. So the first problem, as you can see, is that whenever there's going to be some problems. So we also get some scaling issues when you zoom in and out. You can see that the colors change, right, as we get closer to the object with our camera. But also something else is that we have the aspect ratio of the screen to take into account. And you can see here that as I move my screen, I'm getting some weirdness with the gradients. So let's fix the ratio of the screen, and then we're going to tackle this scaling here, inconsistency. The first thing we need if we want to actually take into account our aspect ratio is that we need to somehow have the ratio between the horizontal and the vertical sizes of the screen. So think about it for a moment. If we have a monitor, think about it like a phone or something. If a phone has 1,000 pixels on its height and 500 pixels on its horizontal axis, on its length, then that phone has an aspect ratio of 1 to 0.5. So it means that the longest part of the pixels represents 1, and the smaller part is half of it, so it's 0.5. So it doesn't matter if the phone is, let's say, 2,000 pixels height and 1,000 pixels wide, it's still gonna work. That ratio is still gonna work. So we don't want to actually use the pixels themselves of our screen. we want to use a ratio that is pixel agnostic. So let's get here a node called view size. And, well, let me get once again to debug Piloto. And you'll notice here, this displays the size of my viewport here. So if I make this, let's say, a little bit longer, you can see these numbers shift accordingly. So let me go back. What we can do here is that we're going to have to turn these numbers of pixels into a ratio, just like what I described. For that, let's break out Piloto components. So now we have the red value and the green value there. And we're going to divide one by the other. This is how you get, and it's going to be a little cross division like this. And we got that. Well, this is not really going to show anything. Here we have now these values that are just really the same. But the thing is, these values represent ratio of this division. What we're going to do is that we're going to append this value here is going to be relative to the red, and what we're going to do is that we're going to set our base value to 1. And now we're going to have the result, once again, debug Piloto values, we're going to have here our ratio. So meaning that one of our as's is 1 and the other is 77% of that in size. So if I try to make this a perfect square here, let me see if I can try and nail this as a perfect square. All right, so now if we get this, it means that our screen is a perfect square. If we get something like this, you can see here that it's the inverse. And we only need one of these numbers to control it, because we know that if the height represents 1.8 of 1, whatever 1 is, we know that the height is going to be bigger than the length of this proverbial phone that I'm kind of using here. So let's go back to a square-ish little viewport there. We have got that. So now that we have this ratio, we need to kind of just add it to our screen position. The way we're going to do that is that we're going to multiply our screen position by the ratio. There is an issue with it. And this issue is, hold on, let me go back here. If we want to shift this, if we want to multiply this, we need their starting points to be the same. We need the kind of UV type of thing to be the same. And this right here, well, you can't really tell, but the UVs are not centered. And we need the screen position. You can see here that the screen position, their UV starts all the way up there. And we want to have it that their UVs starts here in the middle. What we're going to do here is that we're going to do a constant bias scale. And this is probably another video explaining what this node does. But we're going to use minus 0.5. And we're going to multiply it by a scale of 2. And if I look here, preview node, we have the same kind of screen position logic, but now you can see here that if I move it around, the colors meet at the middle. After we have this on the middle, we can keep on going with our little logic here. So we can take our view size, which is like the XY ratio. So I'm even gonna like aspect ratio. I'm gonna even name that so that we know what we're doing. And we're going to multiply our centered UVs, not normalize, we're going to multiply it by our aspect ratio. Now, what we want to do as well is go back, right? So this constant bias scale, we're going to duplicate it here. Of course, this is not going to work because we kind of need to invert the logic that we just did. So we're going to do 1, and we did choose, so we're going to do 0.5. So we're going to have it. You can see here that our values kind of back. Whoa, I'm rotating. Sorry, I'm rotating the plane. You can see here where this went. All right, great. So we have this constant bias scale here. We can put this onto the subtract. But now we also want to do the same thing on this fella here. We also want to adjust it by our aspect ratio. So before this multiply here, we're going to multiply those two fellas together. And we don't need to do the constant bias scale because it was already set up like that from the beginning. Now if we start previewing the node, you can see here that it's actually working. Still have the UV still scale when you get really close to the camera, but now we are no longer getting stretched by our aspect ratio. Let me see here if I can display it here. Let's see. What? Well, camera clip is kind of getting in the way. You can see here that the values, they're scaling up, but they're keeping themselves relatively the same. Alright, so what I did here before we keep going is that I imported these little textures here, these UV textures. These are from the forum Real-Time VFX. I'm going to attach a link on the description for you to get them. But just so it becomes a little bit easier for us to follow. So here we have our little texture here on Screenspace, and you can see no matter the aspect ratio, the little squares remain the same. So it's a little bit easier for you to tell that it's working. But we still have this problem here with the scaling, and this one is somewhat easy to fix, I do think. So let's get onto it. So what I did here also is that I just got my subtract and applied it to the UVs of the texture sample, and the effect is already working. What we want to do here is that we want to take the object position into account relative to the camera position whenever we're scaling things up and down. There's complicated ways of doing that, but a really easy way of doing this is to first get the object position. Oh, what? Oh, I want the object position. So here we have the object position. And then we can transform this position from rolled space, and we're going to put this into view space. So let me just get here, absolute rolled space, and we're going to put this into view space. This is essentially telling you what the position of the object is relative to the screen. This has three components to it. So let me try to do a split. No, let me do a mask. Sorry, once again. I was just done doing some Unity stuff, so I still have the Unity terminology in mind. So let's do some split here, and let's do a debug scalar, I think is the name. Yeah. So now, if I go here and start previewing this node, you can see that we have this value here, and this one is relative to, all right, the x as is. So you can see here that if I put my object right in the middle of the screen, well, I'm not going to nail the exact middle, but it's going to be 0. And the further away it is from 0, the higher the number goes, if it's to the right, and if it's to the left, the lower the number goes. And vertically, it doesn't really affect anything. The only reason why it's changing the number is because my mouse precision is not great. But if I take, for example, the green value, the same thing is kind of going to be true, but now on the vertical axis. So if I put this as close to the center as I can, you can see that it's 0. But the higher it is, the higher the number, the lower it is, the lower the number. Well, guess what? The blue channel is the depth. So how close it is to the camera. So you can see here that if I get really close and personal, the closest I get, the closer and closer I get to 0. Now, the further away I am from it, you can see the number gets higher and higher. So what we're going to do here is that we're going to use this number as a ratio of our scale. So what we're going to do here is that this number is 128. Now, so far, we have only been working with values that are like, 0 to 1. So if we multiply this, if we use this value here, 128, on our UVs, we're going to absolutely decimate them, because that is not the space they use. They use usually a range from 0 to 1. The way we can turn this into a range from 0 to 1 is by dividing it by 1. So, well, actually, we're dividing 1 by it. So we're taking 1 and dividing it by 128. Which yields us 0.00021. This is the value that we're actually gonna use here. now what we can do is that we have all of this logic here, right? And this is a UV. This is a set of UVs. As you can see here, if I start previewing, this is plugged into the UVs and it's working. So what we can do here is that we can use a default node called scales UV by center. And we're gonna, what the hell happened here? And we're gonna put this subtract, which is our UVs, into the UV node, and the texture scale, this thing right here. And now this output, if we put it here, oh my goodness, it's not working. Well, this is way too small. Let me think here. What could I have done wrong? What did I do wrong? What did I do wrong? I don't think I did anything wrong. I think we just gotta scale it, actually. So, oh, of course. No. That's correct. Sorry. So we also want to multiply this by the object radius, right? So that it is adjusted by the size of the object. So let's get here object radius. Whoops. So again, you can't get them all. And let's multiply this by our little friend divide here. And we can see that now we get a number closer to 1. You see? Everything ties together nicely. And now if we preview this, start previewing node, you can see that I can move my camera away from the object, closer to the object, and it's always Screenspace UVs, no matter what. Great. So something extra here, just so that we wrap it up, is that I do actually want to give the ability for us to manipulate the scales of the UV. And to do that, it's very simple. You just do multiply, and if I put here, this works just like any UV would. So 1 is itself. If I do 2, oops, I did 21 by mistake. Sorry. If I do 2, it gets a little bit closer. And if I do like 0.1, for example, we're going to get a lot more of these patterns repeating themselves. So we can kind of expose this as a parameter here, a scalar parameter called scale. And if we put this here, we can put this as a default value of 1. And now we have a value that we can manipulate the size of the UV with, which is just great. Alrighty, folks. So I think this pretty much brings this to a close. Now, all that's left to do is for you to take all of these elements, right, and turn this logic right here into a material function. Once again, I expect to use this logic a lot in the upcoming tutorials, so it's useful for you to have these turned into a material function so that for posterity, you don't have to redo everything every time that we make a new VFX. Let's take one final look here. Oh, look at that. Wait, what? It's not working? How? Did I save you? Maybe I didn't save. Yeah, I hadn't saved. Okay. So you can see here we have the Screenspace UVs, and no matter how far away or how close to the camera it is, look at that. It simply just works. Beautiful, folks. Thank you for your time and attention. See you later. Alrighty, thank you for watching. It's a rainy day, but it would make it sunny if I received a like and subscription from you. Also, let us know what tutorial you want to see next. We're always looking out for suggestions, not only for me, but also for William. So please leave them in the description below. Thank you so much. Don't forget to check out our Discord server, where you can find a lot more stuff about Piloto Studio. You can reach out to me or William directly, and you're going to be on the loop whenever there's a new tutorial coming out. So thank you so much for watching, and goodbye!